And friends, today we have the pleasure and the honor to welcome Professor Wiener Branges from Fourier University in St. Petersburg. And today will be the first of the lecture course of Professor Branges, a course which is entitled A Survey of Hilbert Spaces of Entire Functions, in preparation of the colloquium in Poland. And here maybe I should make just one small explanation, because there will be a conference in Poland in the second half of May, which will be devoted explicitly to the Branges theory, to the theory of Hilbert spaces of entire functions. And this is the colloquium which is mentioned in the title. Please.
I'd like to begin with Euler and the hypergeometric series. This is the creation of analysis as far as I'm concerned. Euler introduced the hypergeometric series for application to his gamma function and also to his zeta function. These are both two different levels of application, and it would be well to stay with the gamma function because it is the source of all the information. Hypergeometric series, the hypergeometric analysis was stimulated in the 19th century by two important factors. One was the discovery of Fourier analysis, and the other, of course, was the discovery of the Cauchy formula in complex analysis. Many people say the Cauchy formula created complex analysis. That's not true. Complex analysis existed long before as power series, and power series remain of great importance despite the value of the Cauchy formula. Now, the application of hypergeometric function theory was made principally in the 19th century with the creation, the discovery of computable orthogonal polynomials on the line. This is a great discovery of analysis that occurred, and it occurred partially here in St. Petersburg. Now, at the end of the 19th century, Stieltjes axiomatized, or he made an analysis of orthogonal polynomials which needs to be understood. Stieltjes studied positive linear functionals on polynomials. This is the creation of integration theory. And I must say that I've studied many books on integration theory, and what the authors do not realize that the first thing you needed to say with an integration theory is to decide what you're going to integrate. And if you don't make that decision, you're not going to have a good theory. The best choice of functions to integrate is not the most complicated one, it is the simplest one. Simple things are what matter in life, not complicated things. Stieltjes studied positive linear functionals on polynomials. A polynomial is said to be non-negative if its values are non-negative on the line. A polynomial which is non-negative on the line I omitted something, but to say a polynomial has non-negative values on the line means that the zeros of the polynomials are symmetric above and below the real axis. And on the real axis, they occur in pairs. You have double zeros. So non-negative polynomials are a computable object in algebra. A positive linear functional is a non-negative linear functional which does not annihilate all polynomials. But if the linear functional does not annihilate all polynomials, it may annihilate some polynomials. And the polynomials which it annihilates form an ideal of the polynomial algebra. That ideal is generated by a polynomial, and the polynomial, the generator, is a polynomial with only real zeros. We can go on. Let's go back. Let's see. We still go a bit more. Okay, a linear functional on polynomials is said to be non-negative if its values on non-negative polynomials are non-negative numbers. Now, if R is a sufficiently small positive number, the set of polynomials of degree less than R are a Hilbert space when you consider them with a scalar product defined by the action of the polynomial, a positive linear functional. Keep going. We seem to keep going on. If for some positive integer r, a positive linear functional annihilates no non-trivial, non-negative polynomial of degree less than r, then you can define a scalar product. A scalar product on polynomials, I call the polynomials fz and gz. The scalar product is written with brackets with a number, and that number is defined by the action of the linear functional on fz g star z. G star z is the conjugate of gz. It has conjugate coefficients. The conjugate of the conjugate of the value is equal to the value of the conjugate. So on the real axis, the values are real. So that would be a positive linear functional. You have a Hilbert space. Now, this Hilbert space is so trivial that nobody thought to examine its properties. Classically, to study a Hilbert space, you constructed an orthogonal set, and you wrote an element of the space as an expansion in terms of the orthogonal set. Now, the trouble with that point of view is nobody's thinking. They're just computing. If there's a space here, we need to know the structure of that space. And a space that appears has certain obvious properties. Namely, if you have an element of the space and it has a zero, say a zero that's not on the real axis, then you can move the zero to the other side of the real axis. You do that by multiplying by a linear function and dividing by a linear function. Now that procedure does not change the scalar self-product, because if you look at the definition is making values on the line, and somehow that doesn't make any difference to the scalar self-product. Okay, that's the first obvious property. I call it the axiom H1. The second property is trivial because we're working in finite dimensional spaces, but we want to have a properties that apply without restriction on dimension. And so we need to know that the linear functional that assigns the function value at a point, at a not on the real axis. We have a linear functional on the space, and since it's continuous by hypothesis or in finite dimensions, every linear functional is continuous. That linear functional is going to be represented in a nice way by the Hilbert space. Now, let's just take the axiom that you have the continuity of linear functionals that give function values. So the point here is that if you have a space of functions, there are linear functionals on the space that matter because you can see them. It's the linear functional that gives the function value. Now, that's obvious, but the point is that mathematicians are very clever people and say they don't see what is obvious. We have to become dumb and simple like children to understand what's going on. The next property is obvious too, that if you take a polynomial and you conjugate its coefficients to make the conjugate polynomial, that new polynomial has the same scalar self-product as the original polynomial. Now these properties apply to an arbitrary Hilbert space whose elements are functions that are defined and analytic in the complex plane. These are called entire functions. So if we have a Hilbert space of entire functions, it's meaningful to satisfy these axioms. And any properties of finite dimensional spaces that depend on the axioms will apply in a space of infinite dimension. So we freed ourselves from finite dimensions by making the axiomatic treatment. Okay, now the structure of the space is determined by the linear functionals on the space. If you have a linear functional on a Hilbert space, it's represented as a scalar product with a special element of the space. That element is often called a reproducing kernel function. By hypothesis, these reproducing kernel functions exist for many elements of the space, all non-real points. And because we have axioms on the space, that reproducing kernel function is not a very complicated function of two variables, but it reduces to a function of one complex variables, or really two complex variables treated as parts of separate functions. There is one function, Ez, which satisfies the inequality, an inequality that says that the modulus of the function above the real axis is bigger, strictly bigger than the modulus below the real axis. So if you have a function with that property, there is a Stieltjes space which has a certain reproducing kernel function that's expressed in terms of that function Ez. And it turns out that, of course, that reproducing kernel function determines the Hilbert space. Now, what's being used here is something which was not very well known when I was a student, and that is that you could have Hilbert spaces with reproducing kernel functions, and that the theory of those Hilbert spaces is immensely simpler than the theory of general Hilbert spaces. So if you work with these examples, you're going to understand something. Now these spaces occur in Fourier analysis, and there's a theorem of Bochner that tells you how to characterize the Fourier transform of a function which has non-negative values on the real axis. And now when Bochner gave that theorem, he didn't tell you why it works. And it works because there's a reproducing kernel function, a space that you can construct as a result of that. And if you're interested in Fourier analysis, you might want to look at that Bochner theorem and learn it. I was a student at Cornell University, in 1956, and some professor was trying to apply that theorem in a general context, and he asked me how to solve a problem that involved that. And as a result of that, I learned what the proof I learned about reproducing kernel functions, and this accident of my career was immensely helpful, almost as good as any technical training that I got from books. Now, a Stiltje space, I think we've gone through this already. Now, if you have a Stiltje space and you have this function, defining function, often you write it Ez equals Az minus IBZ, where Az and Bz are entire functions which are real on the real axis. I don't think I see that formula. Here it is, Ez equals Az minus IBZ. These are functions which are real for real z. They're self-conjugate. And if you know about orthogonal polynomials, you know that they're very important in the classical theory. What the classical theory omits is that not only are the Az and Bz important, but also certain combinations like Ez. They're known, but they're not stressed. Let's take the Bz arbitrarily. This is an entire function whose zeros on the real axis, whose zeros lie on the real axis, and you can make an interpolation formula in terms of, you have an orthogonal set of functions, k of lambda n z. So you look at the reproducing kernel functions where the lambda n are the zeros, and there's a Newton interpolation formula. So the idea is this hypergeometric theory of Euler is a generalization of the work of Newton. And it's very deeply related to that. So the Newton interpolation formula says that if you have a function, you can expand it as a linear combination of reproducing kernel functions using the function values at the zeros. And you have to divide by a constant factor. That constant factor is usually positive. If it's 0, then there's an interpretation of the formula which I won't give, but the formula applies generally with the right interpretation. Now, the closed span of these orthogonal functions does not necessarily the whole space. In fact, in finite dimensions, it often happens that it's not the whole space. It can be, but then you can have a case where the Bz has a smaller degree, and it won't be the whole space. But if it's not the whole space, it's nearly the whole space. The orthogonal complement of the span of the orthogonal complement has dimension 0 or 1. So what we have to think about when we have a space is we have to consider multiplication by z. Multiplication by z is a transformation that takes a function fz of z into its product, z fz of z. But you make that definition when both fz and z times fz are in the space. So from the point of view of Hilbert space theory, we're having an introduction to transformations that are partially defined. I should have acknowledged, and I never did, the sources of this work, but in the first part of the 20th century, people were very concerned with transformations like this. And they usually worked in abstract situations, so they talked about symmetric transformations and self-adjoint transformations and all kinds of complicated things. that you have to spend months, if not years, to master. But if you take a model and you have explicitly multiplication by z in a space like this, you can forget about all the fancy theories. You simply calculate with what's possible. And you have a transformation now that need not be densely defined, but the orthogonal complement of the domain has dimension 0 or 1. Now, this means if we have two, we're given a space, and I call the space the B space. So I put E, B, Z. I don't want a subscript. Subscripts are very annoying. So I make it a separate variable. E, B of Z. That's a space with parameter B. And if we have a space with a parameter B, and if multiplication by Z is not dense in that space, then there's another Stiltze space. That's the closure of the domain of multiplication by Z. It turns out that that's a Stiltze space. So you see, it's advantageous to have the concept of a Stiltze space. It's advantageous to have the axioms, because then you're looking for spaces that have the axiom. You have a purpose, and that helps you succeed. Even if you're very dumb, you're going to get there. Now, we have a new space. If we have a space with parameter B, we get a new space with parameter A. And the question is, what is the relationship? You have a question? What is the relationship between the A space and the B space? The spaces are defined by functions EAZ and EBZ. And we know that there is a function EAZ because you satisfy the axioms. But what is it? Well, we can compute the function. So to compute the function, you have to observe that, and this is a calculation you can make, that when the domain is not dense, there will be a linear combination, a non-trivial linear combination of AZ and BZ, which belongs to the space. And it will span the orthogonal complement of the domain. And the U and V are not arbitrary numbers. The product U bar V is real, so it's equal to U bar V equals to V bar U. And now, the next observation is that with a Stiltze space, the function EAZ is not unique. You can make various choices of functions that will define the same space, but it's always possible to choose the new function so that it also is a linear combination of AZ and BZ. In fact, with the same coefficients. And having that information, you can compute the function EAZ. Now, what happens in this situation? This is a classical situation in orthogonal functions. And in the 19th century, people used continued fractions. And continued fractions are just another way of dealing with matrices. And modern mathematicians usually do not want to work with continued fractions. They want to work with matrices. So you have to reformulate the information of that century in modern terms. And that means that you have to introduce a matrix whose elements are, in general, entire functions. So the matrix depends upon A and B, but it's a function of Z, the coefficients. And I call the coefficients A, B, C, and D. That's a standard notation for matrices. Now, in this situation, you compute those functions, and they are linear functions that are determined by the U and V. So we have the concept of a matrix of entire functions that relates one space to another. Now, at this point in the 19th century, people made a terrible mistake. They weren't looking at Stiltje spaces, they were looking at orthogonal polynomials. And what they missed is that there are other Stiltje spaces present here where you don't have an isometric inclusion. Now, one of the contributions of my career that I am proud of is that I used transformations that are contractive without being isometric. That is, isometric is something that preserves energy. A contractive transformation is one where you can have an energy loss. And it's very important in life, as in mathematics, to have the concept of a contractive transformation. Can you imagine a government that could function where it's always balancing its budget? No. You have to realize that when you're dealing with governments, they're going to be losing money, and they want to control the losses. Then, if you realize that, you deal with the problems. In mathematics, if you realize that you're going to have losses, you prepare for it. And that information allowed me to prove, and it's not verified, that every continuous linear transformation of a Hilbert space into itself has invariant subspaces, but not only invariant subspaces, but in subspaces that are invariant under commuting transformations. That proof of mine has never been verified. And of course, it's possible that it's erroneous. But if you're interested, you might want to look at it. It's available on my webpage. The proof of invariant subspaces is advantageous because it's training ground, preparation for working with Hilbert spaces. It's like if you want to play a cello, you practice with Bach exercises for the cello. And if you want to do Hilbert space and you want something to practice with, I suggest that you learn the invariant subspace theory. Now, there's Stiltje spaces exist which are contained contractively, you can move on now, in the given space. So we have a space A with parameter A contained contractively in a space with parameter B. But there are other spaces in between. Let's say that A and B are positive numbers. For every number T between A and B, we can interpolate, and we can make a new space. Now that new space will be contained contractively in the big space. But the small space will be contained isometrically. When you have a knowledge of these other Stiltje spaces, you have a much easier kind of analysis than recurrence relations. Recurrence relations are very tedious things to deal with. And if you know about the interpolation, you deal with differential equations instead. And they're a lot easier to deal with that. So let's get on to that. I give a lot of details here how to do the spaces. Let's give a picture here, but we have intermediate spaces. Let's go. We don't need the M's, but so we have these intermediate spaces, and they depend upon the parameter. And if you differentiate with respect to the parameter, you have a differential equation with constant coefficients. And of course, that's very easy to solve. And not only do the defining functions, the A and B, satisfy differential equations, but the reproducing kernel function, which is an important feature, also has a differential equation. Now, that differential equation, once you've found it, I mean, this is completely trivial that you have that equation, but if you do this triviality, you learn something. You learn that you could have that differential equation without having linear functions, without having a trivial matrix. In fact, all you need, keep moving in, all you need is a matrix-valued function, M of t, I call it. This is the structure function of a canonical linear system that's being constructed here. And this function, little m of t, t is in some interval, and has entries. It has real entries, alpha, beta, and gamma. So this is a matrix that's symmetric about the diagonal. And we also need to know that it is non-decreasing. That is, in the matrix sense, the matrix, there's the inequalities for matrices, and you have to be able to know that they get bigger as you move up on the parameters. So if you have a non-decreasing matrix-valued functions, then, and if you start with a Stiltje space, suppose that the A space is given, then you can construct the B space, and what you do is you solve differential equations in terms of the alpha t and beta t. I use the prime is for a derivative. Let's assume that we have absolutely continuous functions so that the derivative is good. That's no loss of generality. So these equations have a solution starting with the initial conditions when t equals a, and we go to the solution when t equals b, and we have a situation that generalizes what we had previously. We had a differential equation for the reproducing kernel function that was trivial because we had actually constants, coefficients in there, but you can have variable coefficients and it still works. You still construct, you can construct a new space. So I see I have a mistake on the board here. No, that's good. The B function, the difference in the B functions and the difference in the A functions is an integral. Previously I said, if we go back, let's go back a little bit. You see, B and A satisfy differential equations, but nobody wants to use a differential equation. You have to invert it to have an integral equation. The differential equation there is essential for simplicity, but the integral equation is essential for getting some information out of it. So you invert integrate the differential equation, so you have integral equations, and these integral equations have solutions and they create a new space where the reproducing kernel functions increases or changes by an amount which is given by an integral with respect to that M of t, that structure function. So the space, the A space, is contained contractively in the B space. But the inclusion will always be isometric on the closure of the domain of multiplication by Z. So that's in the A space. So we nearly have an isometric inclusion. We have only a small amount of contractivity. And when you don't have, well, let's go on to that. I don't want to go into too many details here. The point is that you can invert this. If you're given a Stiltje space of entire functions, I call it the B space, there will always be spaces that are contained contractively inside it. These spaces non-trivial spaces that will do that. The existence of these spaces is not my contribution at all. I think Mark Crane probably should be credited for that. But what I was able to show, let's get on with it, is that if you have two spaces that are contained let's say that we have two subspaces of the B space of the same kind. I was able to prove that one space, that the spaces are totally ordered, that one space has to be contained contractively in the other one. This is a theorem that Crane didn't get, and in my book on 1968, I credit a special case of that theorem to Crane. You want to keep going on? Crane dealt with the case, that's the vibrating string it's called, the case where there's a symmetry condition, and the symmetry condition says that when we replace z by minus z, that produces the conjugate entire function for the defining function ez. Or in other words, the az is an even function of z, and the bz is an odd function of z. And I said that Crane had solved that problem in the special case where you had the symmetry condition. But in 1984, when I came to Leningrad, Crane wrote a letter stating that all cases of the theorem were new to him. So that was an error in my book. So that's my contribution to Hilbert spaces of entire functions. I mean, somewhere in your life you have to say you proved a theorem, and that's my theorem. So it's actually rather curious proof of it, and I would be delighted to have another proof. Now, I want to go into another subject. We have to make a break sometime. Yes. This is a good time to make a break. Are we ready? So in my first lecture, I tried to give very basic fundamental principles of a certain kind of analysis that many people are not familiar with. And for that reason, I had to talk at a very elementary level. And I want to apologize for those that were above that level. But we must remember there are always some that are not at that level. And we have to move up gradually to get the level that we want. Now, the next level that we want here is the significance. What is the significance of the Stiltje spaces? What is the significance of the mathematics of the 19th century with orthogonal polynomials? Is it something that we can forget about? Well, I would say that would be very dangerous for the 21st century to forget about the heritage of the 19th century, because at that time people moved much more slowly than they do today, and they thought about what they were doing. And we have a problem in our modern day that nobody is thinking. It's very dangerous. I will not try to talk about politics. That's impossible to deal with logically. But in mathematics, we have the hope of making sense of this world. And let's try to do it. So the purpose of mathematicians in the 19th century was concerned with something like the hypergeometric function theory. How does the hypergeometric function theory impinge upon us? Well, the significance of the hypergeometric function theory is this is something computable. It's something that you can work with and do things with. And if you're not in that situation, you're going to have to rely on a computer to do your work for you. And these computers are terribly, terribly dumb. You think that they're powerful because they have such a large number of brain cells, but the problem is to tell the computer what to do. And unfortunately, that's very difficult. So we want to understand the value of the hypergeometric function theory. Now, we'll start with an example of the Stiltje spaces, which we should be familiar with. These are the Paley Wiener spaces. These spaces were discovered by a young man who died of a skiing accident and brought from England this information about complex number theory as applied to Fourier analysis. And Norbert Wiener had visited to Cambridge, and he worked very effectively with this young man to create these Paley Wiener spaces. Now these spaces are Stiltje spaces, and they have a defining function which is an exponential minus I a z, where a is positive. These functions, exponential functions, have no zeros, but the modulus, the size of the function, increases as you move up on any horizontal line. It gets bigger as you go higher up, and gets smaller, of course, when you go down. So the a function is a cosine function, and the b function is a sine function. It looks like I omitted a parenthesis on the sine az. So, and the m, a, b, z, these are matrices of entire functions that connect the a functions, the b function. They're again equal to trigonometric functions. And I see there's another error, that it should be cosine cz, sine cz. In the matrix, the entries of the matrix, there should be a c instead of an a. In other words, the difference between the parameters. Now, the solution of the structure problem, this is a canonical system that's being generated here, and that this canonical system is determined by a metric function mt, these are multiples of the identity matrix. So you have zeros off the diagonal, and you have equal entries on the diagonal, a positive number t. And everybody knows that there is a Fourier transformation, an expansion of functions on a finite interval that are square integrable with respect to Lebesgue measure and to the Fourier transformation. By the way, I think that this is the best and simplest approach to the Fourier transformation. Essentially, it's a classical approach, and if you look carefully in good books on Fourier analysis, they're going to be doing essentially this to get the Fourier transformation. And so I advise you, if you want to teach the subject meaningfully, that you take this point of view. So keep going. Now, these Paley Wiener spaces have two properties that you're familiar with. Namely, if you have a function that belongs to the space, you can take a shift of the function. That is, if you have a function fz, you can take a function fz plus 1. Now, this shift, this is a shift along the real axis, a real shift. This shift is isometric. Scalar products are unchanged by the shift. And the inverse of this isometric transformation, the adjoint of the isometric transformation is the inverse, so it's the shift in the other direction. So now, the Jacobi spaces of entire functions are a variant of the Paley-Wiener spaces in which you perturb the shift. That is, you have something that a little bit like the shift of a Paley-Wiener space, but you change it a little bit. You change it using a positive number. I call it H. And the Jacobi spaces, there's an isometric transformation that takes an element of the space into itself. So you take Fz into Fz plus 1 plus a constant h minus 1/2 Fz plus 1 minus F minus Z of 1 over 1/2 minus Z. I should have said that there is an isometric transformation that takes Fz into F minus Z. That is, the symmetry condition permits you to reverse the sign on the independent variable isometrically so that this makes sense in the space. And the quotient is designed in such a way that you always do have a 0 in the right place, allowing you to divide by that linear functional. So this is a formula that's meaningful in a space, Stiltje space. And in the Jacobi spaces, this transformation is has an, wait a second. Can you go back a little bit? Yeah, I assume that this transformation is everywhere defined and isometric. Now that property characterizes a space, and you can compute the canonical, the mechanical system, the canonical system of the space, the structure problem, and again, the M of t is computable. You have to use parameterizations with numbers t in the interval 0 to pi, and M prime of t has a tangent in the upper right-hand corner. It has a cotangent in the lower right-hand corner, zeros off the diagonal, and these tangents are taken to powers. Tangent to the 2h minus 1 power and cotangent to the 2h minus 1 power, and it's better to take the argument of the trig functions at 1/2 t instead of t. That makes everything come out nicely, and so then you get a computable Hilbert-Stiltje spaces that are very similar, very analogous to the Paley-Wiener spaces. These spaces were, or the Jacobi expansion was discovered in the 19th century. It wasn't done, of course, with this axiomatic way, but it was very fundamental to the history of mathematics. And here you have a Chebyshev laboratory, and Chebyshev was one of the contributors to that theory. Unfortunately, the expansion is called a Jacobi expansion, and so you don't usually use the word of Chebyshev in that context because it's more specialized what he did. But I need to say that he made applications of the Jacobi expansion, and the problem is that Legendre gave an estimate for the number of primes that are less than a given positive number. There are various formulas, but they're substantially the same. I think that Legendre needs to be credited for the main contribution here. And the problem is, how accurate is the Legendre estimate for the number of primes less than a given positive number? So there's always an error, and you want to know how large the error is. And Chebyshev used what I call the Jacobi Spaces or the Jacobi Expansion to make an estimate of the error. And that estimate is not the best estimate. It's very good work. It's a good use of the special function theory, and it's very instructive. But for estimating the prime numbers, it's not the best way. The best way is due to Riemann, and I'll explain that. And let me go back to the Paley-Wiener spaces. We have the Paley-Wiener spaces. No, we're starting in there. It's the Gauss spaces. So we're moving up, moving farther down.
Up or down?
Oh yeah, we have to go down. We have to go back. Okay, now we have to go further up. It's the Paley. You're up there. Okay. We're.
Yeah.
No, we. So I need the Gauss spaces. Do I have? Okay. Now
This is Paley.
Gauss spaces. This is still these are still Jacobi spaces. This is Paley-Wiener. This is Paley-Wiener. So no.
В обратную сторону, да? Хорошо.
So we're no, you're going too far. You're much too far. You have to go back in the manuscript. Go back. Okay, you've got to go back more. Go back more. Go back more. Go back more. Okay. Yeah, go back even more. Okay. Okay, I forgot to say something about the Jacobi spaces, and we have some members of the audience that are interested in the proof of the Bieberbach conjecture. That in that proof of the Bieberbach conjecture, there is some function theory that's involved in that, and the function theory belongs to the Jacobi spaces. And in 1984, I was so busy with other aspects of the proof that I didn't have a chance to find this application of the Jacobi spaces. And so it's something that hasn't been published or written. But the correct proof of the Bieberbach conjecture should use the Jacobi expansion. And I apologize that that has not been done. Okay, now let's get on to, okay, now we're with the Paley-Wiener spaces again. And in the Paley-Wiener spaces, you can shift in an imaginary direction. You can take Fz into Fz plus I. Now this shift is everywhere defined transformation, and it is self-adjoint. Now the difference here is that we're exploring an entirely new aspect of Fourier analysis. We're moving into the complex domain. And this use of the complex domain is essential for the applications to number theory. It's the motivation for the Riemann hypothesis, or at least I conjecture that's the motivation for it, this possibility. And I certainly does motivate it if you do that. Now the Gauss spaces of entire functions are a perturbation of the shift. So move a self-adjoint transformation. You take a function Fz into Fz plus I, and then you perturb it by adding, again, h minus 1/2, h is a positive number, times, now you take a difference quotient Fz plus I minus F minus Z, but now you have to divide by a new linear function, 1/2 minus Iz. That function you divide by is not arbitrary. You have to find a zero of the numerator in order to divide by a zero of the denominator. So there's not much choice about what you want to do. So in a Gauss space, you have a self-adjoint transformation. And again, the axiom is applied in spaces symmetric about the origin. Now, the spaces are parameterized by all positive numbers. And the solution of the structure problem is m prime of t. Now, you have something like you had before, but now it's the hyperbolic tangent of 1/2 t raised to the 2h minus 1 power, and the hyperbolic cotangent to the 2h minus 1 power to 1/2 t. A very similar formula. The difference is that we use hyperbolic functions instead of trigonometric functions. And again, I should have said this before, the solutions of these functions are hypergeometric series. So these are the main computable examples of Stilche spaces of entire functions. It is very difficult to find an axiom which you can effectively use to determine the solution of the structure problem. It takes a tremendous amount of work to make a calculation for any of these spaces, and I'm glad that I did that. It took years of my life. I had to learn the hypergeometric function theory, and that's very valuable to have this axiomatization of the theory, because not because the axiomatization is in itself valuable, it's because you want to generalize. Now, in Poland, I will talk about a generalization, a very non-trivial generalization of the Gauss spaces, in which the shift is given a property that has a very similar effect to creating the hypergeometric function theory, but it's much more flexible. And I think that that's going to prove the Riemann hypothesis. Now, the next item are the Koomer spaces, or Stilche spaces, which are a limiting case of the Gauss spaces. And here, the space is again symmetric about the origin, but the self-adjoint transformation that takes the space into itself is simply a difference quotient. Again, I mean, this fz plus I minus f minus z divided by 1/2 minus iz. This appeared in the previous axiom, but now you're missing fz plus I. So we were perturbing a shift, but now we're just all perturbation. We don't have the shift anymore. But nevertheless, you can solve the structure problem, and these are the Koomer spaces. Let me say that this man Koomer is not so very well known, I think, but he's a very fundamental contributor to mathematics, because he not only this wonderful function theory, but he also studied the factorization of in integral elements of algebraic number fields. And I think that's very well known, that he did this wonderful contribution. The algebraists know that. But he also made this contribution to analysis. And these spaces turn out to be very, very important for the meaning of Hilbert spaces of entire functions. Now I want to go into a more substantial part of my lecture, and I want to know how much time I have to start in that.
About 20 minutes.
How much?
20 minutes.
Oh, I have a lot of time. In 1884, a mathematician named Nikolai Sonin published in one of the first volumes of Matematische Annalen, published information about the Fourier transformation. that is the motivation for the work on the Riemann hypothesis. It was the motivation very known to people like Hardy and Titchmarsh, but they give that motivation very quietly, and I had to realize that what they sort of put in a footnote or mentioned incidentally was actually the substance or the core of their motivation for their work, which they were concerned with the Riemann hypothesis. I think that Hardy is the most important contributor to the Riemann hypothesis after people like Hermite and Stieltjes, and Hilbert certainly made some contribution there, but Hardy was really a mathematician with very great intuition about analysis. And whenever I work, I continually encounter his name in the things that I do. So in 1884, Sonin made a discovery about the Fourier transformation that deserves to be better known. Now, let me pause for a minute to define the Fourier transformation. I'm going to work on the plane. The plane has a canonical measure, of course, which is the Cartesian product of the Lebesgue measure of the two coordinate lines. The Fourier transformation is an isometric transformation of the space of square integrable functions with respect to the canonical measure, which is defined in some cases by an integral. It's defined by that integral in the case where the integral converges absolutely. That is, you have to have integrability of the integrand, the fc, and the function you get comes out is continuous. And the Fourier inversion says that the inverse transformation is essentially the adjoint, or the adjoint transformation is essentially the inverse. So you can invert the Fourier transformation, and it's essentially the same thing as the Fourier transformation with a change of sign. Okay, now I state all this in very general notation with xc and eta because I want to remind the audience that Fourier analysis has a very extensive generalization. It applies on any locally compact abelian group. Now the problem with that generalization is nobody knows what to do with it. And so I go back to a very fundamental example of the Fourier transformation in order to know what it all means. But at the same time, I want to remind the audience that all these things that are done here have a very extensive generalization. These are constructions that apply to arbitrary or very general kinds of locally compact abelian groups. And let me mention that this Fourier analysis, why it's important. Fourier analysis is important for two reasons in the 19th century or beginning of the 20th century. For one thing, Fourier analysis is the physical theory. It is quantum mechanics. I don't believe that there is any meaningful quantum mechanics that's not Fourier analysis. Now, I'm a mathematician, I'm prejudiced, but my intention is to take all the physics out of it and just leave the mathematics there, and I think it will be a more powerful theory. I haven't done that yet, but that's my intention. Fourier analysis is important for another reason. It's important because it is the formulation of number theory. So when you work with an arbitrary, locally compact abelian group, you're dealing with a construction of things that you may know as zeta functions. And the problem is to know something about the zeros of these functions. So what are the zeta functions? The definition of a zeta function is what you get out of Fourier analysis. And when you get that definition, you get something that is very similar to what happens in the complex plane. So when we work with the complex plane, we do it with great care because we know it applies very generally. Let me say, too, that I believe that quantum mechanics and number theory are part of one theory. That is, a meaningful quantum mechanics is not going to succeed without having the number theory formulation. Quantum mechanics does not apply, in my opinion, in very simple spaces like Euclidean three-dimensional space or some four-dimensional generalization. You need to have locally compact abelian groups. And the significance of these groups is that they treat symmetry. That's the meaning of number theory, that there are certain symmetries that occur in nature that are discrete. They're not continuous. In order to have this number theoretical kind of symmetry, you need these general groups. I would like to say, too, that I became a mathematician because my grandfather was a chemist. He was a biochemist, and he was founder of the Biochemical Research Foundation in Newark, Delaware, funded by a former president of the DuPont Company. And because of the war, the Second World War, I was not brought up in France. I was brought up by my maternal family in America, and my grandfather trained me to be a successor of the director of the Biochemical Research Foundation. So he sent me to the MIT, and at MIT, what I learned is there wasn't any meaningful chemistry there. Nobody knew anything. But something told me that it would be better to do mathematics and learn the mathematics to apply to the chemistry. Now, this has taken many years, but I believe I made the right decision. That is, the structure of electrons in molecules is determined by Fourier analysis. So this is an important problem. We want to build molecules that will do things in medicine and so forth. The way to do it, in my opinion, is to figure out the Fourier analysis and to compute the answers rather than calculate the answers, rather than trying to experiment and compute, making errors in calculations and guessing. There should be a theory of all molecular structure. Thank you. Well, I got carried away with this. Now, when we're working in the plane, there are isometries of the plane of the space of square integrable functions into itself. These are rotations about the origin. A rotation means an element of the space. This is a field. You don't necessarily have fields, but you always have a multiplicative structure in an interesting locally compact group. And what we want is the set of elements that you can multiply, and the conjugate is the inverse. There has to be a kind of a quadratic field, something that you have a conjugation analogous to complex conjugation, and you want that conjugate to be equal to an inverse. Now, these elements form a group. In the case of a plane, it's a commutative group, and if you rotate a function about the origin, you get a new function isometrically, and these transformations commute with the Fourier transformation. So the space, again, I'm doing something very elementary, but I'm preparing for something more complicated, which we cannot cover in this lecture. We had to do in the next lecture. The space of square integrable functions decomposes into orthogonal sum of invariant subspaces under these isometries. And so these subspaces are defined by homomorphisms of the group into the complex numbers. If you have a non-compact group, you have to take finite dimensional representations of the group, but that's no problem. Let's deal with the commutative case. And if the homomorphisms of the complex numbers with conjugate as inverse, you simply raise a number to a power, and that gives a homomorphism of an element of the group into the value as a complex number of absolute value 1. So you have a homomorphism for every integer n, and the space decomposes into functions that are invariant subspaces for these transformations. So there's an invariant subspace for every integer n, and the space, this is the orthogonal sum of these subspaces. Now, the Fourier transformation maps every one of these subspaces into itself, and you also have a conjugation. When you conjugate a complex number, you take fc into f of c conjugate. This is an isometric transformation in the space of square integrable functions, and it commutes with the Fourier transformation, but it does not commute with these invariant subspaces. If you have the invariant subspace defined by n, it maps the space defined by n into the space defined by minus n. For this, because of this symmetry, it is unnecessary to study invariant subspaces when n is negative. Everyone dealing with a subject assumes that you have a non-negative number because the other cases are obtained from that one. Now, the non-negative number is usually called nu in the literature, and I prefer that because I want to use n for other purposes than in work. So, have we come to the end?
Yes, that's all fine.
My gosh, I'm trying. I have a few more pages, but they haven't been copied. So let me talk a little bit generally about the subject in the few minutes that are left. I don't have much time left, do I? How much?
About 5 minutes.
Well, that's right. We're coming to the end of the lecture. So my work here is influenced by the work of Hardy and Titchmarsh. In 1930, they wrote a paper in an English journal. I think it was the Journal of the London Mathematical Society, called Self-Reciprocal Functions. And the idea is that when you consider the Fourier transformation on one of these invariant subspaces, say the invariant subspace is defined by nu for some non-negative integer nu, the Fourier transformation, you have to put a power of I to the nu n, but the Fourier transformation is essentially its own inverse on the subspace if you take a factor of absolute value 1 out of it. And so when the Fourier transformation is considered on the subspace, the element, the space of square summable functions, is the orthogonal sum of a function of functions which are their own Fourier transform and functions which are minus their Fourier transform. Now, the ones that have their own Fourier transform are called self-reciprocal functions, and the ones that are minus their transform are skew reciprocal functions. It's an analogous situation when you work with the cosine transformation or the sine transformation. Of course, that motivates the general case here. Usually the Fourier transformation is called the Hankel transformation in this case, and the Fourier integral reduces to an integral with respect to a Bessel function. This theory greatly influenced my career, and I will try to explain what I discovered about it. And the discovery is basically concerned with the flow of heat. The flow of heat is introduced by Fourier as applied mathematics because I think he thought that Napoleon would like to see it that way. But what he called the flow of heat is actually a very fundamental property of the Fourier transformation. And people rarely use the Fourier transformation directly. They can compute it using the properties of what's called heat flow. Now, the flow of heat, according to Fourier, is something that has to do with a differential equation. And differential equations are not meaningful on locally compact abelian groups. And so there's a tendency for mathematicians who are very sophisticated to think that the flow of heat is something that you can forget about. Now, this is a mistake, because when you have a differential equation, you can invert it to make an integral equation. And an integral equation does make sense on a locally compact abelian group. And so the flow of heat is meaningful on every locally compact abelian group. I think I have to make some small condition, but very general properties of groups are involved there. The flow of heat is a very fundamental discovery because heat flow is always losing energy. This means that there's an operator that generates the flow of heat. I'm thinking of an integral operator, so it's the inverse of the differential operator. But the operator has to have satisfying inequality. And the sum of the operator and its adjoint is not a non-negative operator. You get a self-adjoint transformation, and that's non-negative. So there's something positive, some positivity condition that occurs in the flow of heat. And it applies on a locally compact abelian group. And so the flow of heat is meaningful in almost all Fourier analysis, and it's meaningful for number theory. Well, the flow of heat gives you an inequality. And if you have an inequality, that tells you something about zeros of zeta functions. So I think that the Riemann hypothesis is a consequence of the properties of heat flow. I mean, I'm rather convinced of it. I've gotten very far in my work. I'm sorry to say that I haven't worked as hard as I should, and I'm not there yet. But I feel that this Riemann hypothesis is going to be proved simply by applying the flow of heat to an arbitrary locally compact abelian group. And not only that will be valuable for number theory. After all, who cares about zeros of zeta function? Fourier analysis is something that applies to quantum mechanics. The flow of heat is meaningful for the motion of electrons in molecules. You see, this is a major theory that's been neglected. It was lost in the 20th century, and in this 21st century, we have to catch up on that loss. That's what I'm going to talk about in Poland. Thank you.